Hello everybody. So today I think I'm going to give you some real examples of what Adam's just showed you. What have we been doing with Polyworks in the past probably 6, 8, maybe even 10 years and beyond. So my name is Karl Huckerby. I'm a technical specialist looking at metrology and digital systems in mostly civil aerospace in Derby, UK. So I'm going to tell you a little bit about our products, what we make. We don't make cars in this particular branch of Rolls-Royce anymore. BMW do that. So I'll show you some of them. And a bit of a journey we've gone through all these different steps on how we've got the digital thread and the way that we've approached it. I'm keen to know at the end how you guys have done it, whether you've done a different way around or done DataLoop first, for example. So yeah, there's a few different products. So civil gas turbine engines is one of the main things I've been involved with in the past sort of 20 years. But we've broached out into different sort of technologies, power plants and things across the world really. So we've got big diesel power plant generation, hybrid sort of train systems in Germany. Small modular reactors is all over the news at the minute in terms of powering new generation of energy. There's obviously defence and sort of fighter jets on there. But also we power submarines and a lot of Navy vessels and things as well. So that's kind of, you can imagine, some quite complex engineering in there, some complex parts which need a lot of sort of high-end inspection. We want to make sure everybody goes home safely at the end of the day, and product quality is one of the things that does that. So a typical view into some of our factories. It's like a CMM room, sort of highly temperature controlled, very accurate, really clean sort of environments. But that's not always the type of data that we need. We also need some of the rough stuff from the shop floor next to the machine and all that good stuff. So we're trying to gradually integrate all this data and use it better. We still do a lot of visual inspection. It's a struggle to think about that these days, and how we're going to actually work through digitising sort of visual inspection. So we're starting to look at machine vision, AI, and we've got like an ethical framework called Alethea, which is based around sort of making sure that that's safe and we don't do anything like dangerous with AI. Obviously, what you train it on is really important. So measurement data, is it value add? Is it cost? I'm sure we've all had that discussion, and I think it's value add. I think you've got to use it there, right? You've not just got to pass componentry with a certificate and then just make sure that it's conforming. You've also got to make sure that you're using it. And in an aerospace, it's really important that we get sort of the functional requirements. So what is the product trying to do in service? So these fan blades, for example, spin around really quite fast and power civil jets with sort of crazy amounts of thrust. So we need to make sure that the shape of them is right. We need to make sure they don't crack. We need to make sure that all that data is available for us to do some of that performance management with. I think in the past we haven't really done a lot of that stuff. We make hundreds and thousands of these fan blades, for example, each year, replacing ones that need replacing. But when do we really start to look at, is that dimension correct? Could we change the tolerance? Could we pass maybe a few more? Could we make it do a little bit, eke out that last piece of performance? So we've got this whole sort of infrastructure of shop floor machines, trying to link them up. Programming them is a big cost and a big associated overhead. Manufacturing engineering, trying to move models around and do all that stuff is really complicated. But we're trying to feed all that data back now to design so they could do something clever with the next generation of product. The fan blade there on the right is from the Ultrafan program, which is sort of a next generation gas turbine program with the ATI, so like a R&T program. So the first way we went about this was getting up to speed with the software really, because we generally lag behind with it being so safety conscious. We've got a lot of fixed processes, so I don't think it's unheard of for us to run really old programs, versions of Polyworks, because it's locked down. So There's probably still versions of 2012 running around now, which is not, not proudest moment, but I'll show you why in a minute. So we have been using Polyworks for a long time. I think probably one of the first versions before 2010 when I first started using it, but maybe 2007. But we used to program a macro script every single feature. That became very cumbersome in terms of manufacturing engineering and changing tolerances and things like that. It's really not a place where you want to be. So I started investigating what's this new auto update functionality, how does that work? Putting the features in there, and then I was like, all these features are already in CAD. How do I transfer them across? So I went to the Detroit conference in 2017. I went to Polyworks and said, I want this integrated with PLM, please. So a few years later, it's quite nice to be back here saying we've done all this. We like Polyworks because it's independent. We can obviously run a lot of gauges, different styles and brands, and around the world we've got a lot of different technologies. Some of them companies ebb and flow and are better at different things than others, so it's quite nice to be able to have a central place to store that, and being able to operate that software is really essential. So hopefully that ticks one of Adam's boxes, which is multiple devices. So what's changed? Why are we talking about like model-based definition now, and why is it so important? The first thing is it's possible, right? So we've done a lot of stuff in PLM, been back, we've looked at product manufacturing information. We use NX in Rolls-Royce. I know other people use different PLM packages, but we do use NX, and we've found that you can transfer a lot of different dimensions and a lot of the artifacts that come along with that. So whether it's tolerances, naming conventions, notes, the PMI style, all that good stuff. So we've been working along through lots of different versions of NX. So NX 7, 9, 12, I think, and then now up to 1973. And we've worked through all these different processes. So the ability in Polyworks to consume that GD&T and the CAD model is really good. Hopefully you've tested some of that out for yourselves. I'll show you some examples of that in a minute. But we can't continue to grow. I mean, the amount of different things in these examples is quite interesting, but we can't continue to grow with this kind of overhead of manufacturing engineering. We don't want this to be the job. The job should be that performance, eking out the performance, the quality, and making sure that our experts are working on that rather than creating new inspection processes. It's just boring, right? Nobody wants to do that for the majority of their time, maybe a little bit of their time. And then what we're going to do with the data. So at the minute we struggle with that. It's stagnant swamps of data all over the company, different servers all over the place. So how do we group that all together and take the benefit of that, look for the worst performing features, and then send a bit of a team to go out there and fix that particular area. So here's an example of a really complex component of ours. It's called a front bearing housing. This is a technical package sort of example where one final engineering design, as we work through and we create sort of CNC programs, CMM programs, documentation, quality, all that stuff, we end up making a lot of different documentations. I think all in total there's 4,000 features, dimensional features on here in the end, and we have to validate each one. Maybe we want to, in the end, sort of sample inspect that as well. So making sure that the backbone of this is done properly, executed well, and importantly parametric is where we're trying to move towards. So if you make a tolerance change, or maybe you add a bit of stock metal on the engineering definition, all of our manufacturing operations all automate automatically, and we pass that feature down through here. So yeah, we end up doing a lot of different, we call them stage models, to be able to reflect the inspection and also the machining, fixturing and all that good stuff. But we didn't start at the hardest thing, which is, we normally like to do that, right? So we like to solve the hardest problem first. But we started real simple, got some real simple blocks, tried to figure out how does this work? How do we transfer across a PRT file in its native format into Polyworks? I think we first started to do this in 2016, 2017, something like that. Yeah, and it started to work. We had to create a lot of good and bad examples because you do end up clicking the wrong thing, and ideally this would all be automated in the end as well. So we're investigating things like family of parts and how do you put that parametrically into the PLM system before it then comes across into Polyworks. So we ended up writing a process, lots of different softwares, lots of cross-software functionality. We start in NX, there's some quality programs in there. Then we have to sort of go through. So each step that we did, we sort of trained this out, and we've got real sort of detailed instructions about how to consume features. So we started off here with, again, a simple test artifact, bringing through different features, cylinders, planes, linear dimensions, surface profiles, points, all of that stuff, and they all carry these BCT references, which is a software which uniquely bubbles each of our features. Here you can see, again, we work through, they're all numbered, we're making sure we've got characteristic numbers and names, all the tolerances are correct, and this is just an extract from the training. So at the minute we're having to do human overchecks as well, just to make sure in this early sort of adoption that we don't make any tolerance mistakes. And here's an example of why it's so good. It's quite a complex datum structure with all the holes and the whole pattern there, position and everything. But that just came straight through, file import, PRT file, switch on your features, and you manage to get quite a complex datum structure in there straight away. And then obviously on top of that, there's sort of 3,800 extra features that we want to inspect too. So yeah, it's working really well, consumption. We have found some issues. So sometimes drawing standardization can be a problem. Because we make products with really long lifespan, we want them to be defined the same, even though maybe the definition has moved on. So maybe ASME or ISO has changed, but we still want to extract the same dimension in the old way, just to make sure that we've got traceability from one engine to the next. So that can be quite complex for us. Might not be quite so difficult if you adopt pure ASME and things like that. There is a lot of complexity in there, so because we do a lot of freeform surfaces, that can be quite difficult, and we're not quite at the stage yet where we can just put a 3D surface tolerance on. We obviously have a lot of people issues, so both a skills shortage and then people moving around a lot. It's really quite difficult to keep people knowledgeable in these fields anymore, so we want to be able to train this out very regularly and almost click through the process and work through it very quickly. And again, mentioned lots of different softwares can be quite complex. Not one person can be, if this digital thread is enacted, we've got lots of different softwares to work our way through. You don't need to know the whole software, you don't need a full training course, but you need to know which few buttons to press to get through that. Obviously we're talking about automating the whole thing. So, the next phase that we actually installed was PMI Plus Loop. We've got some limited studies on that at the minute, but I think it's really important to speak about this because the power is really, really powerful at this point. So on the left is an outlet guide vane, OGV. This sits behind the fan blades that you've just seen. And there's 40 different airfoils in that assembly. They're all very similar, but all very different. So we changed the camber, we changed the length of the cord, we changed the twist, and each one of the feet there that you can see where it bolts in, they're all different. So you can imagine there's a lot of programming, a lot of CAD work, all for them to be very similar. So it's quite frustrating when you've got sort of, I think probably there's about 400 features on this, and every single one's different, and you have to validate all of them. So kind of work through a process here about what do we want to do. So you've got to create a CAD model, and we're going to use NX Replacement Assistant to get all of these PMI features onto the CAD. And then when we swap out the CAD model, all of those PMI features will follow the original plane or cross-section which they're attached to. I think I'll show you that on the next one, the next slide. But how do we get a template, which is sort of like a fixed process view? Then we obviously need to do some MSA in terms of if we're going to 3D scan this. And then maybe we're also going to do like a type 1, so we'll do a comparative measurement as well, where we want to store all that data because that's really important for sort of airworthiness regulations. We also do a FAIR, like a first off. We do a PPAP first batch. Maybe there's sort of the first 3 or 4 in there, and then we want to go into production and get all of our data live. So this is kind of like a first, this is our technical package really for inspection. How do we store this data together so people can find it? And we want to democratize that so designers can see what real products look like, because they don't really see that day to day, because the plants can be in different parts of the world. So this is PMI plus loop as an add-in inside NX. We've got airfoil gauges, which are quite a complex thing if you never use them, that generate like probably 30, 40 features each. And they follow the planes that are within the CAD model. So if we were to move the CAD model up, sort of 10 mil, all of them features would follow that. We'd re-extract the nominals and we'd pass that through into Polyworks directly. So it's really beneficial then. If we start to change the design, we add a bit of extra twist, we can extract a Polyworks process in probably under an hour. There's a few tweaks there that we're trying to work with Polyworks to do, but imagine having that, all of your features there ready, you change the design, and then everything just follows suit, and you can sort of inspect it within an hour. It's very powerful. And then the last phase, which is very recent, so this is all deployed probably 3 weeks, a month ago. So we finally installed DataLoop. Now, the way we've approached this is a little bit different to some people, where they might do a bit of a sample sandpit environment. We've gone to full production straight away. So we've gone through 3 very quick IT phases, a development sandpit, a pre-production, and then a production phase. So we've now got, I think, just speaking to Nick, we've got 160 Polyworks licenses. We've got 100 DataLoop licenses, and we've got 25 PMI Plus licenses now. So that's all on the estate now, and anybody can go between our engineering PC or our shop floor machines and create data and upload it, so anybody can find that data. It's quite a powerful thing, right? Our architecture map was slightly more complex than this. This is one of the original ones from a couple of years ago, but it works really well. It's, you click upload, the data goes. You could go onto your other PC upstairs and have a look. So what's next? We obviously want to automate that whole process flow. We want to make sure that we don't miss any steps, that there's plenty of automation checking tolerances, features, making sure everything's in right. Data min's quite a difficult thing, I think, when you change from a 2D drawing, everyone's using sort of manual techniques, and you move through to automation. Data min, you would be surprised how complex that can be. But then, yeah, all the way through to the insights that we're trying to look for. We want gauge results into there, so I'm also working on sort of a lower end solution, I suppose you'd call it, called Smart Workbench. And Ollie, my apprentice, is here today. He's working on that. And that's how can we use Polyworks to operate hand gauges, visual inspection, put all that data that we normally walk past, a quick stamp and a certify. How do we get that into here and spread around the company? There's also AdQual are going to do some of that work on us with us on a program called Replenish, another R&T program. We want Polyworks to get that data which we're putting into here, and we want it to simulate what that might look like on another gauge. Have you considered doing it on this gauge? There's a cheaper gauge available. It's just come on the market. You've tested it on these 3 parts. Would you like to roll that across to these 100 parts that you've got? How fast could it make it if we split 50% features here, 20% features here, and another 10% there. I don't know if that adds up to 100, but you get what I mean. With the main aim being the minimum cost per feature. So how do we go from, maybe we standardize many of our inspection tools. We use a lot of 3D scanning, 3D structured light. That might be the fastest way, but it might also be fast to do it manually because we're not planning on doing many of these parts. We want a price per feature inspected. So once we've got all that data, we're then going to explore datalytics. So does that dimension and that outcome give us the right answer, or not? You know, should we be focusing our efforts elsewhere? I think a lot of stuff in metrology is whoever shouts loudest. Sometimes that might not be the most important issue that we should be following up. So with this, we can sort it by, I don't know, percentage against tolerance, maybe rejections, and figure out which to tackle first. An intelligent feedback to design. So already we've used some simple photographs, collected them on the shop floor with a machine vision camera, put them into Polyworks, and sort of fed them back to design. That's quite a recent thing. And I'm working a lot in the services part at the minute, and part of our organisation where we're looking at engine parts that maybe don't last as long as they should. Customers are complaining a little bit about that, and it's up to us to go and learn why, and I think metrology is the perfect place to do that. Obviously, DataLoop is the perfect place to store all that. So I'm really interested. I'm here today to sort of ask you guys, what are you doing with model-based definition? Have any of you done this? Is this, is this easy to you? Is it sort of child's play almost? Which bits have you done? And how far along the journey are you? Are you automated yet? And did you deploy it in the same way? Did you do it the other way around? Thank you.